Hello, this is my Lab 5 report, where I chose to model the collision of two carts on a low-friction track and compare a VPython simulation to real video data. The main theme here is connecting experimental motion to the momentum and energy principles. The purpose of this lab was to study how two carts move, collide, and exchange energy on a nearly frictionless track. I recorded their real motion, extracted position data using Tracker, and built a VPython simulation to see how the model compares to reality. The main physics principles I used were the momentum principle, particularly as it relates to the conservation of momentum, and the energy principle, which let me measure how much kinetic energy the system kept versus how much was lost. The main result is that the model and experiment lined up really well, demonstrating a significant kinetic energy drop, which proves that the collision was very inelastic. For the experiment, we filmed two carts moving toward one another and colliding, all in the x-hat direction. I used Tracker to get precise x-position data for each frame, which gave me accurate velocities before and after the collision. My system was the two carts, each with a mass 0.5 kilograms, and the surroundings were the air and the track, non-zero but negligible forces of drag and friction respectively. The initial conditions were extracted from Tracker. Cart 1 started at x equals 0.0108 meters moving to the right at about 0.98 meters per second, and cart 2 started at 1.485 meters moving left at about negative 0.59 meters per second. An important thing to note is that both carts had Velcro strips and also weak magnets inside, which means we definitely expected some energy loss due to deformation and non-ideal contact. Here's the actual collision footage from our experiment. And this is the Tracker analysis showing the data points that gave me the average velocities. In VPython, I modeled each cart as a box with mass and velocity attributes and used a time step of 1 millisecond. Since the surroundings exerted almost no horizontal force, the horizontal momentum of each cart stayed constant outside of the collision. And knowing this, we could derive the formula for the position update by using the momentum principle as you see here, which translates to the code that you see on the right. That code is what enabled the carts to move for each iteration of the loop. To model the collision, I added a conditional statement that checks whether the cart centers get closer than a distance L, which represents the combined half-widths of the carts. At that moment, I assign the final velocities based on the averages I measured in Tracker, and then I continue updating positions the exact same way. Throughout the loop, I plotted the positions, velocities, and kinetic energies of both carts, along with the total kinetic energy and energy loss. Those graphs made it very easy to compare the model to the real system and evaluate how much energy the collision actually absorbed. Here's the output of the code. On top is the simulation, to the left are the position and velocity graphs, and to the right is the energy graph. Overall, the computational model closely matched the real motion, with the timing of the collision and the behavior and speeds after the collision being consistent with what actually happened in the experiment. From the output, we find that the initial total kinetic energy was about 0.33 joules, and after the collision, only about 0.05 joules remained, meaning there was a significant loss of kinetic energy due to things like sound, heat, deformation, and the Velcro and magnets. Some sources of error include marking errors in Tracker, imperfect calibration, small friction from the wheels and track, and the inability to directly measure certain inelastic effects. So, what does this mean in terms of the energy principle? For the two-cart system alone, kinetic energy definitely decreases, but the energy principle still holds if we can correctly account for where that lost energy goes. The energy lost curve in my graph is really the energy transferred to the surroundings in the ways I just mentioned. The way we represent energy is very dependent on the system, so if we expanded this system to include everything involved, the track, the air, internal structures, the carts, acoustics, then the total change in energy would actually be zero. In other words, we can broadly say that the energy principle was satisfied as long as we recognize where the energy is going. For my what-if question, I did research to find a way to mathematically represent the elasticity of a collision, so that I could use this to update velocity in my program instead of relying on the Tracker measured final velocities. I learned that I could do this through something called the coefficient of restitution, denoted by E with the formula that you see on screen. I calculated it based on my measured velocities to get a value of about 0.344. An E value of 1 is elastic, and it gets more inelastic as it goes down to 0, so this means the observed collision was very inelastic. I implemented the restitution formulas for one-dimensional collisions in my collision box of code as you see here. And here you can see my original output and the output of this new model. There are some subtle differences in the final speeds and energy since the new model doesn't account for some real-world factors, but the trends are essentially the same, so this restitution-based model is a good estimation of what happened in the experiment. Overall, the simulation and experimental data showed that the collision was strongly inelastic, and the energy and momentum principles accurately explain both the motion and the large loss of kinetic energy. Thank you for watching.